Welcome. We're going to move on this week and we're going to talk about something called the Chinese remainder theorem. So we talked before the break. You had the midterm. I'm still getting those graded. I apologize. My work computer literally crashed as I got back from my trip, and I haven't had a chance to access stuff the same way. And I'm just now starting to get access back to some of my previous materials. So, so I'm creating a lot of this from scratch. I appreciate your willingness to work with me. So the Chinese remainder theorem we have to have, and I'll explain the reasoning for it actually later. I'm going to start with it because it still is the idea of we're dealing with modular arithmetic. So let's switch up to this idea. So this theorem, Chinese remainder theorem, is all about remainders in different congruence classes. So suppose I have something in mod 4 and something in mod 2. How do I deal with those? So let's look at some different things. I want you to see the pattern about how these things work. So if I just were n, let's just look at all the different numbers, 0 through 10, in mod 2 and in mod 4. And I want you to look at this and ask the question of, what's the pattern that you see? So pause the video for a second, think about that for a second, and what is a pattern that you see? Well, there's a lot of patterns you could see, and I really would love to hear, and I'd encourage you to post and think about it. One thing I see is, for instance, if they both turn out to be 0 over and over and over again. Also, notice that if this top one is 0, then the bottom one is either 0 or 2, but 2 mod 2 would be 0 as well. And in fact, 3 mod 2 is 1. Okay, so we kind of see a pattern that these things, and every 4, they repeat and regrow. That's great. But what happens if we have something a little bit different? For instance, what if we have this? So I'm keeping the top table, and I'm now swapping out a bottom table. We have 2 and 3 because 2 and 3 actually have no common factors, whereas 2 and 4 obviously do. Well, now what? Well, obviously they both have 0 in the first spot, but now when there's a 0, no, these zeros for 2 and for 4 don't correspond to the zeros below. But there's zeros here. When do they occur? At 6. Okay, and then notice it repeats over and over again after 6. So how do these parts in between here compare? So obviously at 0, we're good. 0, we're good. This has a combination of, if you notice, all 5 of the pairs, when n is 1, 2, 3, 4, and 5, are all different. 1, 1, 0, 2, 1, 0, 0, 1, and 1, 1. 1, 2. It turns out that is all the different possible combinations of these. If you just talked about all the ordered pairs, where the first element is coming from 0, 1, and the second element is coming 0, 1, 2, there'd be 6 of them, and it turns out that 0 through 5 happens to correspond to all those possible combinations. Well, this pattern, starts getting us thinking about this idea. And so, does this pattern continue? Well, the pattern above didn't quite continue. It was a little bit different. And the reason being 2 and 3 are relatively prime to each other. It's actually not because they are prime numbers. They are prime, but they're relatively prime to each other. And that is a key critical idea. So we actually have a lemma that we get from this, and here it is. If you have two numbers, n1 and n2, have the same remainder, mod b, and a divides b, then n1 and n2 have the same remainder, mod a. Okay, wait. So let's come back up here. 2 divides 4. So to kind of illustrate this, 2 divides 4. What are two numbers that have the same mod in terms of mod 4? Well, let's just take 2 and 10. Since 2 divides 4, they both have the same mod, mod 2, namely 0. So when they divide, that's obviously the same thing. Come down here. This is mod 2. This is mod 2. That doesn't work. So because it doesn't work down here when they are not, when 2 does not divide 3, then we run into a slight problem. But it turns out that this lemma, which is really useful, is actually going to help us get to some place that we can talk about in a second. So let's try an example to show you how this lemma actually is still useful. Let's take 6 and 4. So let's suppose that n is congruent to 1 mod 6, and n is congruent to, the question is, what can n be mod 4? Well, we can't use this lemma because, let's go back to the lemma, a has to divide b. Well, 4 does not divide 6. So this lemma doesn't seem to make sense, except we can actually consider the fact that 2 does divide both 4 and 2 divides 6. And this is better than trying to do brute force, because you would literally have to try n is 0 all the way to 11, because 12 is the first lowest common multiple of both these numbers, besides 0. So obviously when n is 0, they're both 0, but that's not true. And then after that, we start looking more at this. So what are the possible mod 4 values that come up? Well, let's just look at this. Let's look at 2. Since n is congruent to 1 mod 2, then n is congruent to 1 mod 2, since 1 mod 2 is 1. Okay, so I am going to use this now. So again, just coming back up to the lemma, they have the same remainder. In fact, so if n1 and n2 have the same remainder mod b, then they have the same remainder mod a. What that also tells us is that we can leverage this to our advantage. So we're now going to use, we're looking at all the things that have this. So all the possible remainders mod 4 are 0, 1, 2, and 3. Now, only 1 and 3 are congruent to 1 mod 2, because we're looking for a number that is congruent to 1 mod 2 if it's congruent to 1 mod 6. Because the lemma kind of just told us that, again, if you have 2 values, since 2 divides 6, if a number is n is congruent to 1, then it must be congruent to 1 mod 2, which is still 1. And then we look at all the possible values of this, and 0, well, this mod 2 is 0, 2 mod 2 is 0, but 1 mod 2 and 3 mod 2. So these are the only possible ones we can examine. So let's consider what are those mod 4 when they are 1 mod 6. So we can actually look at it as both of them, and we can actually then test it out, and it turns out that it's both of them. The reason being, again, so what are the values of, so I'm gonna write down here. So if n is congruent to 1 mod 6, well then let's think about all the values. And I'll just brute force it again. I'm just going to show you at 1. Here's my n value: 1, 2, 3, 4, 6, and then 1, 2, 3, 4, 5. I should say this is 0. So this is the first 12, and this is n mod 6, and n mod 4 would start off at 0, and you go 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. So let's just look at where these are up in the mod 6. And it turns out the corresponding values down the mod 4 are 1 and 3. And that's an easier way to do it, is simply take a greatest common factor of the two values and utilize that. Well, that's great. We're talking about a lot of things, but what if they're not? So this is where the Chinese remainder theorem is even heavier, because what happens if the greatest common divisor is 1? Well, then, because I'd come back here and I'd have mod 1, and that's every number is mod 1, and that doesn't quite work. But that's actually kind of what this says, that if you have two modular amounts, A and B, that are both, their greatest common factor is 1, they're relatively prime to each other, then for any remainder A, mod A, and any remainder B, mod B. So our two values we have to care about, A mod A and B mod B. Then there exists some integer out there that n is congruent to r mod A and n is congruent to r mod B. And any two such values are congruent to each other mod A times B. So first off, there is some number for which they satisfy both congruences. That means there is a solution. And if there are two such solutions, then they're congruent to each other mod the product of AB. All right, let's see what that looks like, because that sounds like a lot of stuff, and a lot of people are like, wait. That sounds like weird. This actually allows us to solve essentially systems of modular arithmetic when our mods are different mods. All right, so let's look at an example. What's the smallest positive integer n such that n is congruent to 3 mod 11 and n is congruent to 7 mod 17? Now, these are relatively prime numbers. If you want to do this brute force, you have to do 11 times 17 different combinations and check all of those values. That's really not looking up, not looking for that. So we don't really want to look at it that intensely. So let's start looking at it differently. Since they have the greatest common divisor of 1, we can apply the Chinese remainder theorem, which going back tells us there exists something and its solutions are congruent mod the product. So A times B is 187. Okay, we got that. We'll save that for later. Next, we're going to actually solve the following linear congruences. This is where this actually gets funky. And by the way, a bunch of this actually comes from the proof of the Chinese remainder theorem that I did not give you. You can look it up and so forth. The proof is actually what gives us the power to solve the ability to do this. So the theorem is awesome, but the proof is actually where the algorithmic idea comes from. Hence why the proof's really useful. So what I'm going to do is I'm going to solve 17. What's the multiplicative inverse of 17 mod 11? That's my first one. Secondly, I want to solve 11. What's multiplicative of 11 mod 17? We know how to find these inverses because, well, we've been doing this a lot. So let's do it. First, to solve this one, well, that's 6. We can just do this real quickly. 6 times y is equal to 1. And then we just quickly break this down. 5, 4, and work our way back from greatest common. So this is, notice I am using the, I'm using this to find the number 2, because 2 is my multiplicative inverse by using the extended Euclidean algorithm. So we're using extended Euclidean algorithm, which that's really nice. So my first y1 is 2. So again, coming back up here, I have to solve these two equations. So we've now solved that y1 is equal to 2. All right, we have that. Perfect. To solve the second one, we're again going to do the extended Euclidean algorithm. So to solve this, we essentially are just doing this and this, which is just going to give us 17, which is 11 times 1 plus 6 more. Move the 11 to 6, get a remainder of 5, which give you a remainder of 1. Remainder of 1, we're done because we never can get smaller than 1. So because of this, we can now flip everything, work our way back out, and it turns out that, notice it's -3 times 11, but -3 is congruent to 14. So y2 is 14. Okay, so we've now found y1, which is 2, y2, which is 14. Now what we have to do to solve this is actually kind of crazy. So again, what we have done essentially, I'm going to rewind all the way because I really want to help you understand all this, and then I'm going to show you how we're going to play this. We started off by simply finding what was the greatest common divisor. It's 1. Boom, I can use the Chinese remainder theorem. As soon as I have the Chinese remainder theorem, I need A times B, which is 187. And then I'm going to solve these congruences to find y1 and y2. Why? I will show you in just a minute. This is where this gets really, really cool. So we have all this. We come here, and we have found our y1 and y2. So again, these were our systems of modular arithmetics. The solution, this is where it gets interesting. So I'm going to point out where all these numbers come from. So this first one, the 3, it's coming from here. 17, it's coming from here. Where did the 2 come from? We'll go all the way back, and we had, remember, 17 times y1 was congruent to 1 mod 11. So that means that this portion of the entire thing is congruent to 1 mod 11. So I'm taking the 3 times this, essentially this solution right here. So this is the mod 11 situation, which 3 times 1 and would just be 3, but it's in the mod 11 world. Then over here, the 7 is coming from this mod 17 desired value, but the mod 11 is coming here, and this was y2. So in other words, what is this? So let's say I have a system of equations where n is equal to a. I shouldn't do a for that one. Let's do a c. Let's call it x1, better yet. Yeah, let's call it x1. All right, so we're going to call this x1 mod a, and n is congruent to x2 mod b. Then we need a y1, a y2, and b y1. When are these congruent to 1 mod a and mod b? So notice I have them switched so that they are opposite of the mods. When I solve them, the y1 is connected to the b, and the y2 is connected to the a. See that right there? So what this is going to do, it's going to be x1 times by1 plus x2 ay2. And this is going to be our solution that we are going to work on. All right, I'm going to make that all go away, take a screenshot, look at it. So when we do this, calculation's easy. It's this, which is 1,180. But that, again, mod 17 times 11 is only 58. So it turns out that that is our solution, is 58. And we can check that because 58 is 11 times 5 plus 3 more. And 58 is also 17 times 3, which is congruent to 7, mod 17. Okay, so let's just kind of rewind and let's kind of come back up here, and I want to show you something to help you understand this reasoning as to where all this came from again. So from here, let's say if I took this and I took it mod 11. Well, this part right here would be 0 because it has an 11 in it. This mod 11, so 17 times 2 mod 11, we've already established that that is congruent to 1. So this is going to be 3 times 1 mod 11, which happens to be 3. Now, what if we go back and do the whole shebang over again, but this time, instead of mod 11, we do mod 17. Well, then this whole portion is 0 because of the 17. And this product is going to be 1 mod 17 because of how we found it. So this is 7 times 1, which is 7 mod 17. So that's how we built this up to be this number, was we had to take this and then we went ahead and we calculated this value and took it mod the product of A, B. So our 58 turns out to be our answer. So that is kind of the key thing I want you to focus on and utilize. This is Chinese remainder theorem. Now, you're going to have to practice this part of this discussion board. Here's your first three problems. I'm going to write the fourth problem in just a second to help you understand the motivation as to why we care about it. Problem one, if n is congruent to 5 mod 9, what can it be mod 3? If n is congruent to 1 mod 6, what can it be mod 5? And the last, if n is congruent to 2 mod 10, what can it be mod 6? So again, I don't want you brute forcing these things. You'd have to run through a whole bunch of different options and some other things, but look at them. And also remember the Chinese remainder theorem is only when they're relatively prime. So you're gonna have to ask that question. If they are relatively prime, use the Chinese remainder theorem. If they're not, we use that lemma that we did earlier in the class, that we did earlier in the video. So rewind and go back to that. All right, so let's get to the motivation. So we did this. Why? Well, remember the Diffie-Hellman at key exchange and the Elgamal public key encryption relied on the fact it's easy to compute powers of a to the n mod p. But it's difficult to recover the exponent n if you only know a and you only know a to the n. That's what this is all dependent on. So the difficulty of that is all based on the fact that, but it also at the same time, we can analyze the security of it because of Fermat's little theorem. Fermat's little theorem tells us that the property if I'm taking something mod p, and this is easy. So again, we're taking mod prime, done, a to the n. If it's 1, then well, I kind of know what n is. But if it's not, well, I can start raising it to different powers, and there's still some different stuff. But these are all used on, I'm raising to a power that the power is the unknown part. Well, what happens if instead of using a prime number, I use a modular number m that is not prime? So it's a composite of two numbers or more. Is it still true that a to the m minus 1 is congruent to 1 mod m? So for example, just to illustrate this, what this question is asking is something like, is a to the, yeah, let's go 98 congruent to 1 mod 99? Because we know that 99 is equal to 3 times 3 times 11. So is that for every a value I can pick, is this true? Because that's true for the Fermat's little theorem. And it turns out it's not true. We can pick some values real quickly and see that this does not hold true. It'll cause all sorts of headaches. And that is why we actually have a massive problem on our hands. Because RSA encryption is going to rely right now on mod something that's not prime. So we're now stuck in a massive problem. So what do we do? Well, let's look at some information. And this is where I want you to, we're going to want to generalize Fermat's little theorem. And we're going to get to that later this week. But I want you to think about, first off, an example about understanding the powers if it's not prime. So let's take 15. We know that 15 is a product of 3 and 5. So because it's product 3 and 5, I just want you to look at this. What's obviously 1 to any power, still 1. 2, what do you notice? 3, what do you notice? 4, what do you notice? 5, what do you notice? 6, what do you notice? 7, what do you notice? Go down the list. Is there any patterns that you're seeing in any of these rows or columns? And then we can start asking questions of why. Why are we getting patterns at certain times? And what are those patterns exactly? So is there any patterns in terms of columns, in terms of rows? And I want you to look at that and say, what is a pattern you see here? Like I can see one pattern, and maybe you all, like, here's an interesting point just to point out. In the row with, let me get my check marks, put stars instead. Here, here, and here, you might just notice that all of them have the number squared. It goes the number one, the number one, number one. It just keeps bouncing back and forth. That's interesting. So we want to know a little bit more about this. We want to know, why are these playing out that way, but not the other rows? That's actually a pattern. What other things can we see that we can take away when they do have a one? Like, do any of them have a one, for instance, in the n cubed row? Do any of them have ones in the end of the fifth row, besides one, obviously? Okay, so look at those patterns, answer that. That's your challenge for the discussion board. Let me know what questions you have. Good luck.